You accept the big paychecks and
Paychecks.
those things. Okay, so I'm going to do a little bit of review
like, 20
first
bucks
of all
an hour.
of stuff that you may be completely unfamiliar with, or if you have some familiarity, it's maybe just a little bit, and that's what's called summation notation.
Can you read them on? Just, okay, yeah.
There we go. All right, so what does that symbol usually mean when you see it mathematically?
Sum of.
It means sum. Yeah, we use it, it's a capital sigma, and we use it generally when we want to write sums. And so I want to do a little bit of review because we're going to be using this notation today a whole bunch. And then when you get to Calc 2, oh my gosh, it's like a third of the course you're using this kind of notation. So if I said something like this, I equals 1 to 5, 2i plus 3. It's like, what the heck does that mean? Well, first of all, I is called the index. How many have written any type of computer code? Okay, day one computer code, a do loop. What do you do? For I equal 1 to 10, do.
Well, or for I equals 0, I is greater than 10,
Yeah,
I plus plus.
You do something by, that's called a counter or an index. And the thing is, it starts at the lowest number and increments how? By 1. And then it stops at the high number. So the way you'd read this is, start with I equal 1 and put a 1 in there. And what would that be?
5.
That'd be 5. Now put a 2 in there. 7, okay, good. And a 3?
9.
When do I stop? I stop now. And what do I do with these values?
Add them.
I add them. That's it. This is shorthand notation usually when I got to do a lot of stuff. And in other words, it looks scary and it seems evil, and you know, I always attributed this notation to that kid that got picked last in kickball. Remember that kid? The girl on the crutches with the broken leg who always got picked right before that guy? I mean, he was really, really terrible. And he invented this to get back at all of us. That's what people think. No, actually, this is brilliant. What if I wanted to do 500 numbers? I can represent it with one statement. You see, if I'm doing this on a computer, I'm having the computer do all the work, but I've got to tell it what to add. So summation notation is shortcuts for doing fairly big problems. I don't care what the numerical answer is. I want you to be able to interpret this correctly. So that's what this means. So if we did a couple of different ones, okay, suppose I had the following. I'm going to go from I equal 1 to n, and I'm going to call it AI. This is my AI. AI is whatever I want it to be. It could be I squared, it could be I to the 4th power, it could be the sine of I. It's something involving I. This is A1 plus A2 plus all the way up to AN. I'm adding up n terms. Now what if I wanted to go 1 to n of some other thing? Well, we'll do sort of the same thing. Okay. I want to add these two summations up. And by the way, the fact that they're finishing at n, these are finite. These are finite summations. They're not infinite. Next semester, you're going to deal with infinite and infinite only. But you're going to use all the rules that we're going to talk about today so that I can make conclusions later on. Well, I'm going to add those two quantities up, right? I'm going to say A1 plus A2 all the way up to AN plus B1 plus B2 all the way up to BN. But I'm adding a bunch of numbers. And we know addition is commutative. We know addition is associative. Commutative means I can rearrange. Associative means I can regroup. Could I write it like this? Stare at that for a moment. Is that true?
Yes.
I rearranged and I regrouped. But wouldn't that make this the sum from I equal 1 to n of AI plus BI? So this is the first and very powerful proof. We just proved that the sum of the summations is the summation of the sum. Does that sound familiar? The sum of the limits, limit of the sum of the derivatives, derivative of the sum of the integrals, integral of the sum. Haven't we been using this all the way along? Yeah. So that there's probably a partner that goes with this one. What do you think that would be? What's the other thing that applies to limits and to the derivatives and to the antiderivatives? The sum and the
Difference. Product.
specifically not products in general, but scalar multiples, constants, constant multiples, right? We know that the limit of a constant times a function is a constant times a limit. We know the derivative of a constant times a function is a constant times a derivative. We showed that the integral of a constant times a function is a constant times the integral. What about if I wanted to do this? Well, according to what we just said, that should be Ka1 plus Ka2 all the way to Kan. But if I factor out the K, but that's just K times, ooh, that's exactly what we were hoping, isn't it?
Yes.
I only need these two properties to be able to do a whole lot of stuff, and that's what we're going to do today. We're going to do a lot of stuff that uses those two things. Now, by the way, do notice, this is important, both of these sums started and ended at the same place. Is that important? Well, if they don't end at the same place, I really can't group them together. So they have to begin and end at the same place. You're going to do all of this stuff next semester, and you're going to do it with infinites. But it doesn't change how you do things, okay? Because it's still the same basic thing. That the sum of the summations is the summation of the sum, and the summation of a constant times is constant times the summation. Now, with that, I want to throw a few identities out to you that it's unlikely you've seen these before unless you had an intermediate algebra or pre-calculus class that actually spent some time doing summations. Maybe you did, maybe you didn't. There's four that I want to introduce. Now, n is just finite. N could be anything you want it to be. It could be 10, it could be 1,000, it could be 1,000,000. Just, it's my stopping point. These are the only ones that we typically really care about mathematically. We use all of these at various times. Now, let's start with the first one. Isn't the first one, I start with 1 and now increment by 1, but it's just a 1. It's not changing, is it? So what's the next term? And then the next term? How many times?
N times.
N times. What does it equal?
100.
Just, yeah, that was kind of boring. If I add up the number 1 n times, I get n. Oh, okay, that makes sense. The next one is very common. It's very powerful. 1 plus 2 plus 3 all the way up to n. Okay, this one comes with a story. Now, the story I'm going to tell you is a legend. It has been passed down for centuries. Legends aren't necessarily absolutely factual, but they don't have to be. In other words, they illustrate a point. Okay, I trained and I taught martial arts for 40 years. Okay, the founder of Japanese karate in the United States and Japan, Gichin Funakoshi. Anybody ever heard that name before? You know, he's written many books. He's the one that brought from Okinawa to Japan in the 1920s, and then American servicemen after World War II learned it in the 40s, brought it to America. There's a legend that he was practicing his stances on his roof and during a hurricane, 70, 80 mile an hour winds, and he couldn't be knocked off his roof. And it's a classic story, so they're teaching the certain stances. And I remember when I read that in his autobiography, I'm laughing. Now he was probably just drunk and wandered onto the roof and did all he could not to get blown off the roof and killed and attributed it to his great karate. Probably not, but it's a great story. It's a legend. Well, I'm going to tell you the legend of my favorite famous mathematician, okay? Little Carl Friedrich Gauss. He's my favorite mathematician because he contributed, one of the most important contributors to calculus, but more importantly, he is the founder of linear algebra, all things matrix theory. How many have ever worked with matrices? You ever use terms like Gaussian elimination? Yeah, Gauss is the one who's literally everything that we know about linear algebra he's credited with. Super, super genius. But he grew up in a time when they were in the one-room schoolhouse, all the kids, all ages in the same schoolhouse, and they didn't have pencils and paper. It hadn't been invented yet. So what they had, there's their own little easels, little chalkboards, and their piece of slate. I kid you not, this is how schools work. Paper wasn't readily available, for another century or two, okay? And pencils, maybe a couple centuries away. So apparently, as the legend goes, he's a child. And as the legend goes, he was being particularly obnoxious one day. You know, smarter than everyone in the room kind of stuff. And the teacher told him, go add up the first 1,000,000 positive integers. That'll keep him busy for a while. Problem is, he comes back a couple minutes later with an answer. And he was correct. They didn't have good calculators then, by the way. The calculator was a big sandbox, and you had a stick, and you drew your math in the sandbox. There was no technology. We're talking a couple hundred years ago. So the question is, how did he do it? In other words, it's the derivation of this formula. It's what's called an arithmetic sequence or series, depending on how I'm listing it. So he does something like this. He's going to add up all these guys. Dot, dot, dot is my favorite mathematical symbol. You know. So how the heck did he do it? Well, he made an observation. He said, well, what if I do this? What if he added the numbers in reverse order? If you remember doing sequences and series in algebra pre-calc, you did this. This is called an arithmetic series where you're adding the same amount each time. And it produces a very simple formula. If I add them in reverse order, what do I notice each of these sums add up to?
1,001.
They all add up to 1,000,001. Huh. They all add up to 1,000,001. And how many of them do I have?
Million.
I have 1,000,000 of them. Is that the answer?
Yeah.
Well, you're half right.
Half of them,
Why is it half of that?
because you're grouping things.
You just did it twice.
Yeah.
And so this is the answer. And that's what he figured out in a couple of minutes, a child. Pretty smart kid. Now again, he might have been 30 when he figured this out. I don't know. When I'm told the story, he's a young child. I like that story way better. And being the obnoxious snot, I could totally relate because that was me in school. Right? I used to get kicked out of the class pretty much every day. I was never in class at the end of the day. And I'd get picked up at the principal's office basically every day. And I can relate. So this has a formula. What was 1? Well, 1 is 1, that's duh, but what was a million? That's my n. So the formula is n over 2 times n plus 1. This is often referred to as Gauss's formula. There's a lot of things called Gauss's formula. This is one of them. Isn't that cool, though? It's brilliant. So if I wanted to add up the first however many positive integers, I only need to know how many of them do I have? And we just did it. Cool. The next one's a little more complicated. I'm not going to derive it. In Math 245, discrete math, we do a lot of proofs. How many remember probably in pre-calculus, doing proof by induction? Does that sound familiar to anyone? You derive all of these formulas typically using proof by induction, and it's not real complicated, and it's a really beautiful way to introduce the topic. But the next one is n plus 1, 2n plus 1, all over 6. And then the last one's easiest to remember because it's just the square of that one. So it's n squared, n plus 1 squared over 4. Now, we are going to use these to help us answer certain questions today. That's why I'm telling you these now. I don't need you to know these. You're not going to use these again in Calc 1. You will use these again in higher level classes, and you'll just review them before you use them. Don't even sweat it, okay? So keeping all these in the back of our minds, now here's the question that I have. And this is where we're going with calculus. I have some function y equals f of x from A to B. And I want to find the area of this region. Now, let's assume that this is not a geometric shape that you're familiar with. That curve could be anything you want it to be. It could be a sine wave, it could be a parabola, it doesn't matter. But it's not a line segment, okay? This is not a quadrilateral. So I want to find this area. Well, that's not an easy thing to do. A and B can be any real numbers, but for today, let's keep it simple. Let's just make them be integers. So then it's going to be easier for you to conceptualize. We can tweak them all we want as we go. So what I want to do first of all is I want to divide this up evenly into partitions. Now the term partition is a word we use all the time in calculus, but you might not be totally familiar. This building was being built, okay? The floor, very important structurally, right? The ceiling, very important structurally because there's still stuff above us. But the walls, structurally, they could be made of paper for all we care. They're not holding up anything. So when the floor was built, was this wall there? No. Was that wall there? No. There were no walls going this way. These walls are called partitions. They section off the room. That's it. That's all they do. It's not real complicated. So I want to create a partition. But I want all my partitions to start as equal widths. So imagine I'm going to do the following, right? I'm going to subdivide this n times. I'm going to do my best to make these look like they're the same. Okay, pretend these are all the same. N could be anything from 2 to a bazillion. But then the next thing I'm going to do is make rectangles. And I'm going to make rectangles by taking the right endpoint, very specifically the right endpoint, and then squaring it going across. Now, look at that picture for a moment. If I find the area of each of those rectangles, which is actually going to be a very, very simple thing to do, will that equal the area under the curve? What do you think? Will it equal the area under the curve? No. Will it be close?
Yeah.
Yeah. We'd say it's a reasonable estimation. And this is a squiggly line. This is an estimation. This is definitely not an equals. How could I possibly improve upon my estimation? More cowbell. More rectangles, right? So if I subdivide this again and again and again and again and make rectangles progressively skinnier, it would get better. You guys smell it? It smells like
Integration.
lemon. It smells like a lemon. But we're not there yet. So let's find the finite areas. You with me? So if we call this x0, then this would be x1, this would be x2, and so on. This will be xn. I said there are n partitions. So somewhere in the middle here I have I minus 1 and I have I. I'm concentrating on this one right here. This is the ith rectangle, right? First, second, third, and so on. This would be the nth rectangle. This is the ith rectangle. Now, the width of the rectangle, that's my delta x. Anytime you're finding the change in something, doesn't matter what it is, right? If you're in a chemistry class and you're finding the change in heat, which way do you always subtract? Always. Change is always what?
Bigger. How far?
It's 60 degrees when you got up, it was 80 degrees by noon. What was the temperature change?
20.
20. It's 80 degrees at noon, but it's 40 degrees at midnight. What's the temperature change? 80 to 40.
Oh, 40.
Well, then that means it's 120 degrees at midnight. Come on, guys. If you can tell me from 60 to 80 is 20, you can't tell me from 80 to 40?
40?
No, that would be 120 degrees.
Minus
Negative.
Change is negative exactly how often?
Half the time.
Half the time. Come on. Nothing would cool down. Prices couldn't go down. You couldn't lose weight. No, change can be negative, but how do you always measure change? You always measure change the same way.
Minus initial. Final minus initial.
Yeah, ending minus beginning. There's no exception. If I subtract in the wrong direction, I'll have the opposite sign. So when I'm finding the change in x and then moving left to right, then it would be this one minus this one, wouldn't it? Now, in my picture, the change of x is all going to be positive. If I was doing changes in y, would they all be positive? No, because sometimes it's going up, sometimes it's going down. But I'm only interested in the change of x. So delta x1 is simply x1 minus x0. That width is delta x1. Delta x2 is x2 minus x1, and so on. But I said we were going to partition this in such a way that all of the widths are exactly the same. That makes it a lot easier. Okay, exactly how many rectangles do I have?
And,
So you're saying with enough, no, say it. N.
N.
I have n rectangles. How wide is my interval?
B minus A.
B minus A. If I had a, let's keep it real simple. If the width of my interval was 100 units and I had 20 rectangles, wouldn't each one be 5 wide? 100 divided by 20? I have a width of B minus A and I have n rectangles. So how wide is each rectangle? That wide. And we're going to call this delta xi because all of them are the same. They're all exactly the same. 1, 2, 3, 4, all the way up to the nth one. They're all this wide. This is a constant. A and B are known ahead of time. N is how many rectangles I have. Now, I'm going to take a limit at some point, and the limit will be as n grows, isn't it? Okay? So keep that in mind. So now let's go back to here. What is the height of my rectangle? Because I want the area of that rectangle.
Y.
Well, it is a y value, but how am I going to find it? So we're going to have to plug in the x coordinate. Well, that's not going to be trivial. Well, maybe it will be. x0 is a. Let's write down what we know. x0 is a. Isn't x1 a plus exactly 1 delta x? And all my delta x's are the same, so I could just call it delta x if you want. What's x2? Oh. What's the ith one? That's the one that I need. That's going to be a plus I delta x's, which would be a number because I already calculated delta x is a constant, a is a constant. You know, a might be 3, and delta x might be 5. It doesn't matter. We said the height of this rectangle, I simply put in the x value. And that's the x value, right there. So the height of the ith rectangle, f of xi, is going to be f of a plus I delta xi. Now that looks terrible right now, but we're going to do a specific function in a moment, so you're going to have numbers. It's not going to be ambiguous at all. What is the area of the ith rectangle? Well, isn't area base times height? And the base is the delta x. So let's call it a sub I. The area of the ith rectangle would be that height times the width. I now have a number. This is a specific number in mind. That's the area of this one here. So if I said I wanted to do a reasonable estimation of the overall area, then you would say the area can be loosely estimated. That's A1 plus A2 plus A3 all the way up to AN. That is the area of all n rectangles. It's a loose estimation because we agreed it's not going to be exactly the area. But let's suppose that this function was really complicated and you had a computer. Could you just say, have the computer do 1,000,000 rectangles that are all paper thin? Mm-hmm. And by the way, it would do the entire problem in seconds. The numerical value you got at the end would be pretty darn close to the actual answer. In fact, it might be accurate to several decimal places if that's what I was interested in. So we could actually do this entire problem without ever using calculus. But I want to come up with the exact answer if it's possible. So there would be a limit involved. But this is what I'm going to do. So how will I get A? I'm going to take a limit. Specifically as n grows without boundary. That's going to be my limit. And then I'll be able to say what A equals. But I can't do that until I actually do the whole problem. So now we're going to do a very specific problem. It involves these guys here. Again, this is a stepping stone to get to the next thing. Because as we're going to see, integration involves sums. It always involves sums. So I want to find the area under a curve. And I'll come up with a fairly simple curve. Let's suppose I'm starting with f of x equals, how about, I don't know, let's say 2x squared plus 3, and my interval is from 3 to 6. How's that? So first thing I want to do is draw a picture that's sort of accurate. I want to go from 3 to 6. Again, it doesn't have to be a perfect picture, but so let's say there's 3 and there's 6. How's that? So I want this area here. Is that a familiar geometric shape to you?
Yes.
It is?
Oh,
Bounded above by a parabola? Huh.
maybe.
I'm not familiar with that shape, but is there a well-defined shape there? Yeah. Do we know its area? No, because that's not a rectangle. We don't have any formula for that. But we're going to do what we just did. So the first thing is we're going to subdivide this. We're going to subdivide it n times. Just, you don't have to do 1,000 rectangles. Draw enough so you can actually see what's going on. Okay? And we're going to take the right endpoint. Now, the reason we're going to take the right endpoint is actually really clever. I didn't come up with this. We're taking the right endpoint because it's much easier to describe the height. Because if I take the right endpoint, then the height is equal to the, so in other words, this last rectangle that ends at 6, what's its height? F of 6. If I take the right endpoint, then the x-coordinate is the one that I'm actually using for the height. Does that make sense? If I had used the left endpoint, it'd be more confusing. If I had used the midpoint, it's even more confusing still. I'm using the right endpoint. Now, in my picture, would it be safe to say that the area under the rectangles is greater than, equal, or less than the area under the curve in this picture?
Greater than?
Greater than what?
It's hanging over.
Because it's still coming up with a
Yeah, these all spill over, don't they? If my curve was moving all over the place, then it's probably kind of a wash, right? If my curve was going the other way, maybe it's less than. But right now, I think it's safe to say that if I just found a finite number of rectangles, I'm going to get a reasonable estimation, but it's going to be probably a little bit too big. That's okay. What I want to do now is do what we just did. So the first thing we're going to do is calculate our delta x. And whether you said delta x or delta xi, it's the same thing because they're all equal. Okay? And that's going to be the width of the interval divided by the number of rectangles. So that's simply 3 over n. That's my b minus a over n. Well, that was easy enough. Now, what did we show a moment ago? That the ith coordinate, I'm starting at 3, and then I'm adding 1 delta x, and I'm adding 2 delta x's, then I'm adding 3 delta x's, then 4 delta x's, and eventually I'm adding I delta x's. So this is going to be 3 plus I times 3 over n. Where does the 3 come from in front? Because I'm starting here. Everybody got that? I'm starting here at 3. That's where the 3 from. So I'm starting from there. Now, let's do a quick check just to make sure. If I is 0, that means I'm on the very first line segment. And if I is 0, 3 plus 0 is 3. Okay, that's cool. Now, what if I'm at the very last one? What if I is equal to n? What's n times 3 over n? 3 plus 3 is 6. So that's a quick check that I didn't mess that up. I got the first and I got the last. It's cool. That's the x. I now need the height. So I need f of xi, which is f of 3 plus I times 3 over n. And by the way, it doesn't matter if you put the I in front or after or even in the numerator. That doesn't make any difference. Where's that going to go?
plug it in.
Now that I have a specific function, I'm going to replace x with this quantity. And I'm going to get 3 plus I times 3 over n squared times 2 plus 3. Now I would like to expand that, get everything cleaned up. All right. So this is going to be 2 times 9 plus 6 times 3, so I times 18 over n, plus the last one squared, which would be I squared times 9 over n squared, plus 3. So that's 18 plus, I'm going to put the I now on the other side. I think it'll read, oops, I think it'll read a little bit easier. So it'll be 36 over n I. And then this one would be plus 18 over n squared I squared plus 3. So finally, let's add the 18 and the 3. So this is the height of the ith rectangle. And I can do this for every value I going from 0 all the way to n, okay? Now, the last piece, I need to find the area. All I need to do is take that height and multiply it by the delta x, which is pretty simple in this case. So the ith area the ith area would then be this quantity multiplied by just the 3 over n. And that gives me, what, 63 over n plus 108 over n squared I plus 54 over n cubed I squared. This is the area of the ith rectangle. It looks kind of horrible. And finally, what I'm going to do is add up all the rectangles. Wait. So now I can say that A loosely is the sum from I equal 1 to n of that. Now, in this problem, n is a constant. N is the number of partitions. I is not constant. I is my index. It's my counter. I is going from what? 0 to n. Right? So I is going the whole gamut here. But n is a constant. N is, you have 100 rectangles, let's say. Right? That's my n. Didn't we just come up with a formula for sums and scalar multiples? Didn't we just come up with a formula that said the sum, I can pull them apart and put them together? We did. Can I make this into 3 summations? I mean, I just showed you that one a minute ago. Or sorry, I one minute. What's the last one? 54 over n cubed I squared. I know this is true. But didn't we also show that we could factor out scalars? I is not a scalar. I is the thing that's changing. But n is a scalar. So on the first one, can I write this as 63 over n times the sum of, I don't know, 1? How about the second one? Could I write this as 108 over n squared times the sum of I, which I have over there? And the last one, could I write this as 54 over n cubed times the sum of I squared? Well, definitely not, right? No. First of all, do we agree that this is true?
Yeah.
Yeah, because those are the only rules that exist for manipulating the sums. But we have results for each of those sums, don't we? We have actual results. We can replace each of those sums with an actual result. Whoa. Let's do that. This is 63 over n times what? We just added up the number 1 n times. Is that n? These are going to cancel. What's the next one? The next one's 108 over n squared times what? n plus 1 over 2. Notice I have an n squared on top and an n squared on the bottom. That's a good thing. And then what's the third one? 54 over n cubed times n plus 1, 2n plus 1 over 6. Oh. I could manipulate this. Could I cancel stuff all over the place here? Will everything cancel? No, but a lot of things will. A lot of things will cancel. What's this going to be? 63. Can I cancel one of the ends? What will this now be? 54 times what? N plus 1 over n, because I canceled one of them. 54 and 6, how about 9? Can I cancel one of the n's? Yes. Then what will that leave me with? N plus 1, 2n plus 1 over n squared. So far so good? By the way, we haven't taken a limit. If I have n rectangles, then this is exactly what the area of the rectangles is. Exactly. As n increases and increases and increases, we sense there's a limiting thing. So what I want to do is I want to take these and play with them a minute. So first of all, can I rewrite n plus 1 over n as 1 plus 1 over n? Can I do that?
Mm-hmm.
I want to do that. I really want to do that. So this is 54 times 1 plus 1 over n. Now this is the next one's a little bit more of a clever move. I hate to erase them. I need the space. So over here, the second one is n plus 1 times 2n plus 1 over n squared. Could I write that as n plus 1 over n times 2n plus 1 over n? Is that the exact same thing? Yes? And then could I do the exact same thing? Oh, 1 plus 1 over n times 2 plus 1 over n. We're getting somewhere. We haven't done any calculus yet, by the way. It's coming. I can say with absolute certainty that the area under the rectangles for a finite number of rectangles is exactly this. Now notice I have 3 transient terms, don't I? As I increase the number of rectangles, what's happening to these terms? They're getting small. But they're all positive, aren't they? Do you know what they represent? Each of these guys? The overage. But if I cut the number of rectangles and I made them all smaller, 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 wouldn't my overage get smaller and smaller and smaller also? You know, if I put 1,000 rectangles on there, the overage would be microscopic after a while. There's still an overage, but it's getting smaller and smaller and smaller. So can you tell me exactly what the area is? Yeah, it's going to be the limit as the n approaches infinity. And I'll write it this way. I'm going to be lazy, because that's what this is. And what will that be? Well, as n approaches infinity, won't this term approach 0? Won't this term approach 0? And won't this term approach 0? And what will that leave me with? 63 plus, all right, it's 54 times 1 plus what? 9 times 1 times 2. And I think that's 135. Turns out that's exactly the area under the curve. But the curve doesn't have a geometric base, you know, it's curvy. But we just figured out by using summations, by using rectangles, and by taking a limit at the end, that's exactly the area under the curve. But that was not really fast, was it? That was kind of long. But it's correct. But it was kind of long. So maybe there's an improvement on this. Now, I love this because it's so beautiful and we could do this. But notice these formulas here. We have the constant, we have the I, we have the I squared, we have the I cubed. That corresponds to my original function being a polynomial. Do you see a potential problem with this method for all things?
Yes.
What if it's e to the x? What if it's sine x? What if it's log x? this ain't gonna work. Because we don't have summation formulas that involve sines, cosines, e's, and logs. This only worked for polynomials, but it's a starting point. Remember I called it a stepping stone. But you with me so far? We just figured out a way to actually calculate an area of something that doesn't have a formula by doing, you know, basically rectangles and then taking a limit. So now we're going to go above that. I gave you two very artificial conditions here. First thing is, tell me about the widths of my rectangles. They had to all be equal. What if we removed that as a criteria? And what else did we do? We said we're always going to evaluate from the right endpoint over. What if we remove that as a criteria? In other words, what if we make this a bit more random? Turns out that's where we actually want to go. Question? No. Oh, okay. So, we change the question, and this is going to get crazy on you. Because this is actually how we do it in general, the next thing. This was very specific, and I said we had to do it this way. Equal widths, right endpoint only, so that our heights we could easily calculate. So now, what if, I'm going to give you, same thing, A to B, and I'm going to partition this just like I did before, except I want it to be completely random. It's literally, I'm going to hand everybody in here, I'm going to hand you a marker, and you're going to make your first rectangle. So Max, of course, goes exactly to this spot here. And he says, I think I want to use the midpoint. So Max. But then he hands it to Chase, and Chase says, no, I'm going to make mine really fat. And I'm going to make it from here. I want it to be completely arbitrary and random. And then Tristan says, you guys, you're just too serious. So I'm going to go from the left end point, and I'm going to go here. And then we keep up this process, and, you know, and then somebody else decides, I'm going to go here, and then maybe this person's going to go here. Would you say I was random in my widths? Mm-hmm. Would you say I was random in where in the interval I actually figured out the height? Mm-hmm. Yes. And this is the rule now. They both have to be able to be random. Now here's the crazy part. When I said everything had to be the right endpoint and they had to be equal widths, then it's virtually impossible that the sum of these areas could ever actually equal the area under the curve. I went completely random on my widths and my heights. Do you know it's actually mathematically possible now? Although not really likely, it's possible that if you found the area of each of these rectangles, it could actually be the area under the curve because of the random nature. Isn't that crazy? Now, let's suppose the area under the rectangles isn't exactly the area under the curve. Can I still subdivide them to get closer? Yes. But now I am not putting any conditions on my function. I could only use that if my function was a polynomial, and very specifically, I could only use those if it was a polynomial of degree 3 or less. That's kind of a huge restriction, isn't it? Now I'm saying this could be anything. This could be a sine wave if you want. It could be exponential, it could be inverse trig, it could be anything. I just need an f of x. So let's do like we did before. Let's say that that's xi minus 1, and let's say that's xi. Problem is, I'm not calculating the height anymore from xi. And I'm not doing from xi minus 1, I'm just doing it from some random place in the middle of the interval. So let's call that random place, for lack of a better name, I'm going to call that w sub I. W sub I could be the left endpoint, it could be the right endpoint, or anything in between. But it's the place in the ith interval that I calculate the height. That's why it's a wi. In the first one, that's going to be w1. In the second one, it's going to be w2, and so on. Okay? So what is the area of this rectangle now? This ith rectangle is exactly f of w sub I times delta x sub I, where all of my delta x's are different. Is it possible that some of them could be the same? Sure, but it's not a requirement anymore.
So is it now half? Like, is the area now half for that?
No. How do you calculate the area of this rectangle? The height times the width. I'm just now calculating the height from a random place as opposed to from the right endpoint. So in other words, the height is no longer calculated from f of xi, it's calculated from just some random value in the middle of the interval. Where very specifically, wi is between xi minus 1 and xi. Could I use the left endpoint? Yes. Could I still use the right? Yes. More likely, some random place in between. Now that's kind of crazy. Okay? We're almost there, folks. Almost there. So now, I can now say the area can be loosely written as the sum from 1 to n of this new height. Okay? Now, the value of x, I usually throw in there, x is ranging between what and what? A and B. I need to take a limit. But the problem with taking a limit as either n grows without bound or your delta x is approaching 0, both kind of serve the same purpose. If I said, all right, here's what I want you to do. I want you to take this last rectangle and I want you to subdivide it infinitely. Great. Is that going to give me the area of the whole thing? No, I kind of need to do what? Subdivide the last one only?
The entire interval.
Yeah, I got to do all of them, but how do I do that? How do I say that delta x is going to 0 and at the same time so is that one and at the same time I can't do that. I can only have one thing going to 0, so we have a problem. So we've invented a very clever notation, okay? I'm going to write the notation down. A equals the limit, something's going to happen. We know there's a limit. We just kind of saw that coming. But of what? I can't say as delta x approaches 0. The notation is this. Double bars around a P. P stands for partition. But more specifically, how many have ever seen the double bar notation before? Has anyone here worked with vectors? We use double bar when we want the length of a vector or magnitude. The word there's a word that's associated with that, it's called the norm. How many have heard of norm? Norm in vectors often refers to the magnitude, but it's a more loose general term because I'm not using vectors. The norm of the partition, the norm refers to the largest width. The norm is the largest width. And I'm saying, see, the P is the partition. I partition that up. The norm of the partition is the biggest width of my partition. Now, but if the biggest width is going to 0, that means I took the biggest one and I subdivided it. But doesn't that mean there's a new biggest width? So here's how I explain it every semester. There are people in my Calc 3 that are still dealing with this. You know, they're still getting therapy because it was kind of traumatic. I got to explain what's going on. It'll all be okay in the long run. It's going to be a little scary at first. I'm trying to join the evil league of geniuses. And to do that, there's a few things you have to have. You have to have the evil layer. I have one. You have to have the evil weapon. I do. It's a shrink ray. It's a gigantic shrink ray. And the way it works is I find the biggest person in class, that might be you, Max, and I shrink you down to 1 point. And I'm actually going to do this. Now, by the way, I just got to pour water on you later and you'll come back. But most of those folks in Calc 3 are still kind of traumatized. So I'm going after the biggest person. Who's the smallest person in here? Raise your hand if you're a small person. Okay. Will you be the biggest person at some point?
No.
If I've shrunk everybody else down to 1 point, yeah, at some point you're the biggest person and then you're going. So at some point now everybody's 1 point. This is exactly the mathematics of what I'm explaining. You're taking the largest one and subdividing it infinitely and now moving on to the next largest one and subdividing that and then moving to the next one. So in the end, someone said you have to do all of them. Will we do all of them? Eventually we will do all of them. If I go after the biggest person in class, I shrink you to 1 point, now there's a new biggest person. There's always a new biggest person until everybody's been shrunk to 1 point. Yeah, by the way, the water works on like 98% of you. There's a few that had got lost to the universe, but you know, it happens. You know, they call tolerances and things. So I'm going to do this. I'm going to shrink all these down. This is now equal. You're never going to actually do this as a calculation. This is the explanation of what physically is taking place. We're going to now redefine this quantity. This has a name. And if you've had calculus before, it is a very important name. It's called the Riemann sum. Every integral that will exist the rest of your life is set up this way if it's something you're setting up as an application. Not I gave you an integral and asked you to evaluate. No, you just do. I'm giving you a scenario, you've got to set up the problem. There is a Riemann sum in every problem. What we learn to do is fast forward so that we can skip to the end as soon as possible, because the Riemann sum we are now defining as the integral of f of x dx, same f of x, and we say in words, from A to B. A was the left, B was the right. This is what is called a definite integral. What you have done over the last week and a half is I gave you an integral and I asked you for an antiderivative. I asked you for a function whose derivative was your integrand. So you're working backwards and telling me where it came from. That's called an antiderivative. Integration was to produce the antiderivative. Your answer was a function. Our goal here is to come up with an answer that is not a function, but a scaling. This is a numerical value. Now, how we evaluate this, you gotta wait, that's next thing. Sorry, the how to evaluate it is a whole class. It has a really cool name. Anybody know what it's called? I think it's next class, let me double check. Yeah, it's kind of important. It's called the fundamental theorem of calculus, and it's generally considered the most important work in human history, period. Everything math, everything physics, everything engineering came from this. You don't have, Einstein's theory of relativity without this. And this was actually contributed by many people around the world at similar times independently, which is really incredible. A whole bunch of people were working on this literally at the same time, not talking to each other. It's how we make the connection from simply an antiderivative to an actual calculation. And that's what next class is. Okay? Today is the stepping stone. So our goal is, if I can consider this subdividing rectangles geometry, I'm not going to actually calculate any of these. I'm going to do this so I can set up a problem that eventually produces an integral. Because down the road, you're going to be doing problems where I'm going to say, find the area bounded by these curves. Or I'm going to take these curves, I'm going to rotate them around the x-axis to create a three-dimensional volume. And I want you to find the volume of that shape. I want you to find the surface area of that shape. I want you to draw around it and find the arc length of that shape. These are all things that we're going to do that involve integration. But we can't just start, we have to set up the problem and build. And the setup will always start with the Riemann sum, but you'll learn how to fast forward. You will learn how to, in some cases, almost go from question to setup. But there's a lot of things in between, and that's part of what today is. Okay? Questions so far? So the Riemann sum is the physical subdividing without any rules. This had rules. But because this had so many rules, it was also extremely limiting, right? We could only do a handful of problems. I can do this with anything. Okay? So let's do one. Let's set one up. Let's suppose I want to find the area. Oh gosh, that's toast. Yeah. Under one hump of the sine function. So if we draw a picture, well, I know what the sine wave looks like. It goes like this forever. I want to find the area under one hump. So is that what I want? Makes sense. I probably need to know that value. What will that value be? Now, what is it from here to here?
Pi.
So what's it from here to here?
Pi.
Pi. Yeah, it makes it easy. So my x is going to go from 0 to pi. So if I subdivide this, and then I make a whole bunch of rectangles, it doesn't have to be a perfect picture, then my Riemann sum, I'm going to say, okay, there's wi, there's xi minus 1, there's xi, and that's wi right in the middle. So that height is f of wi times delta xi. But my function is the sine function. Oh, so what's f of wi? That'd technically be the sine of wi. And then I'm multiplying by delta xi. So that would be the ith area. Sorry, a little crayon. Can we now write the Riemann sum? Yeah, I don't need to do anything else. There's no calculating, there's nothing. So I can say this, I'll write the whole thing. Area equals the limit as the norm of the partition approaches 0. That simply means the biggest rectangle is approaching 0, therefore all the rectangles that follow it will also. That's the way, that's the clever way we get all the rectangles going to 0. Now, if all the rectangles are getting infinitely smaller, then do you agree that the over-under that you achieve is also going to 0? I notice I have no over and under if everything's getting smaller and smaller and smaller. Of the sum of this. This is the Riemann sum. Can we now write the definite integral that it equals?
Zero and pi.
0 to pi. So over here somewhere we really should save this, by the way. We kind of need to save this part because that tells us what these are. 0 to pi, those are called your limits of integration. Now it's kind of a strange choice of word. Limits of integration. They're scalars. You're not taking a limit. They are quite literally the endpoints of your interval. Your limits of integration are the endpoints of your interval. I think we could have chose a better word than limits because it sounds like, well, limits. That doesn't involve, the physical taking of a limit. Those are the endpoints. Okay? Now, we don't know what the answer is. We're going to be able to do that soon enough. But if I wanted to subdivide this up into a bunch of rectangles and then calculate the height and then add them up, we could do that. We physically could do that, and we'd get a reasonable estimation, but it'd be some ugly decimal. We don't care about the estimation. We want to know how to do the calculation, which is coming. Okay? Questions? All right, I think this is a good stopping point because we got a whole lot more stuff to do, so let's go do that. Good job.
Hey,
Okay.
I did it.
We are now going to continue on to the next thing, and we're going to discuss a few rules about definite integrals and some of their properties. So I'm going to start with some really simple pictures. Okay? Now, if I ask for the area under this curve, let's go directly to the definite integral. We know that the area is equal to this. We don't know how to calculate this yet. That's what we're going to learn next day. I just want to be able to state this. So that's the area. It's a big deal. That was fairly simple. Okay, here's what I'd like to do next. Can you express this area as the sum of areas? Do you agree that the answer is A1 plus A2?
Yes.
That's. I want this to be an oh duh. I want this to be like, yeah, shut up. Okay, so let's write that as integrals. So that would be A to C of f of x dx plus C to B of f of x dx. So the first thing I want you to notice is the limits of integration. This one ended at C, this one started at C, and when I put them together, I got that one. Does that seem pretty self-explanatory? In my picture here, clearly C is between A and B. Okay, so let me go over a couple small things. Tell me what you think about this. I reversed the limits. Now, the f of x referred to the height in the Riemann sum. I did the delta x's, all adding them up from left to right, taking the higher number, subtracting the lower number from left to right. So we began at the far left, we ended at the far right. What am I doing here? I'm going from the far right to the far left. So what would that mean for my delta x's?
Negative.
They would all be the opposite, wouldn't they? They'd all be negatives. So for that reason and that reason exactly, this is a true statement. This is an absolute, this is always true. If I reverse the order of the integration, it does this. Similarly, what if I put the curve below the x-axis? What if the curve was completely below the x-axis? Then wouldn't curve to x-axis in that subtraction, wouldn't that be a negative height? So in other words, I can get a negative answer to an integral if my curve's below the x-axis and I'm doing that, or if I'm reversing my order of integration. We can change things. So I want you to keep that one in mind. Next one.
Zero? Is it one?
Why would it be 0?
When you're going from just the area of A to A, so.
So basically, I'm asking you for the area of that line
There's
segment,
nothing.
which has a width of
Zero.
0. Ooh. Do you think that's helpful to know that?
Yes.
Does it come up a lot? No, but you're going to be in circumstances where all of a sudden you see something like this emerge and you go, oh, okay, I know what to do. I can manipulate things. So, if I asked you the following question, I've got the integral from -1 to 3 of f of x dx, and I'm going to add that, the integral from 3 to 7 of f of x dx. Can I write this as one integral?
Yeah.
What integral?
-1 to 7.
Does everyone agree with that? Yes. It is not uncommon that you add integrals, but it's actually more common, believe it or not, that you might pull them apart for various reasons. But this is true, because we just demonstrated it right there. Okay, that's cool. All right, new picture, completely unrelated to the last picture.
Mm.
I'm going to put B in the middle this time. Do you agree that this is the big area?
Mm-hmm.
Yes.
And it should equal yes?
Mm-hmm.
Can you isolate this one? Well, if I isolate that one, what will it be? It'll be this one minus this one. Okay, this is just simple arithmetic I'm doing. This is not calculus. So I'm just taking that, I'm going to go a to c of f of x dx minus b to c of f of x dx. Okay, great. Huh. What did we just say right here? If I reverse the order of integration, it changes the sign? Just for fun, because that is our main goal. What if I go C to B?
Be a plus.
Then it would be a plus. Oh. Well, that's interesting. Okay, go back to this picture. I drew a picture where A and B were the outer limits, and I just made C some random constant between A and B. And we said the integral from A to C plus the integral from C to B was the integral from A to B. And that's as close to an O does we're ever going to get. Now I made you a very different picture. I put A and C as the outer limits and B is just some random number in the middle of the interval. And what did we just conclude about the integral from A to B? Isn't that the same thing we just said over there?
Yeah.
Does it matter that B is in the middle? No. We just proved a very powerful mathematical statement. Well, I need a different color for this one, obviously. As long as we picked up where we left off, the answer is just A to B. It didn't matter this time that B was in the middle. This statement is always true, regardless. Isn't that crazy? So let's do an example where we have numbers. I've got the integral from -4 to 8, and I want to add that to, let's say, f of x dx. and I want to subtract the integral from -4 to 5 of f of x dx. Well, according to what I just said over there, wouldn't that be the same?
Switch those and so it's a 5 and -4.
Well, if that doesn't look goofy, nothing does. I got the smaller number on top. That doesn't matter. What do you notice? Five to -4 plus -4 to 8. Can I write that as one integral?
Mm-hmm.
What would it be? I'll do this part. I'm going from what to what? From 5 to -4, then picked up from -4 and went to 8. 5 to 8. Yeah, look at our examples. Whoa. Now, if I drew this as a picture, I think this will be even more obvious. How do we start the problem? -4 to 8. Sorry, that's a little hard to see. And what did we remove? We removed this. What were we left with? Does that make sense? You can see it geometrically. You're like, oh, that's totally cool. I can monkey with integrals as long as the limits of integration match, but only through addition. Okay, when I rewrote it as an addition, this one ended where this one began, which is why I can now say it's 5 to 8. But then I just drew it geometrically, and that makes perfect sense that you can do that. We will use this to our advantage occasionally, not all the time. But it's a manipulation rule that will always be true with definite integrals because you're talking about numerical values. Now, if I asked you to take a derivative of a function, I give you the function, there's no interpretation. It doesn't have to represent something. If I'm giving you something and I'm asking you for a rate of change and now you're having a physical thing, like, the rate of change of the volume per time as we're inflating a balloon, right? That's very specific. If I give you an integral and I say evaluate, anything's fair game because it doesn't represent any specific problem. So if I said evaluate this integral and your answer is a number, positive, negative, 0 are all fair game. There's nothing wrong with that. If I, down the road, I'm going to say find the area, find the volume, find the arc length, find the surface area. That answer has to be positive because it's of a physical object. And so that's where the setup is critical. But in general, if you're integrating something, any answer is fair game because it doesn't have to represent anything yet. You're just going through an exercise. That'd be kind of like me giving you a whole bunch of numbers as you're a kid. Here's a whole bunch of numbers, add them up. You add them up, but I got a negative answer. I must have done it wrong. Well, what if I gave you a bunch of negative numbers? There's nothing about the answer that means anything. You just went through an exercise. So in this case, we're manipulating something to basically get used to how I can manipulate integrals to make them into one or to pull them apart if it's necessary. Now, there's one more major rule that we need, and this is one of the biggest things we're going to use next day when we derive and prove the fundamental theorem. And this is the mean value theorem of antiderivatives or of integrals. Now, we've already had a mean value theorem, if you remember. That's the one I called the rolling rule of one, right? Where we said, as long as I am differentiable and I have endpoints, there is a tangent line that is parallel to the secant line I can draw. There's at least one tangent line, okay? That's what the mean value theorem for derivatives said. There's a mean value theorem for integrals that has nothing to do with that one. So I'm going to give this setup first off. All right, so I have a shape. Okay, again, I keep doing the same picture over and over again. If I asked you what is the area that is bounded by this region, or we usually just say it, the area under the curve. That means curve to axis. Then we know the area is equal to the integral from a to b of f of x dx. And the assumption here is that we will be able to do this problem seamlessly and easily next day. So maybe the answer to this question is 100. Whatever the answer is, that's what the area is. Here's what the mean value theorem of integrals says. We have a numerical value that is equal to the area. I want a rectangle that has exactly the same area. I have a base here. Can I just use that? Sure. So let's just say hypothetically that I can really do this well. Maybe that's the rectangle. Let's suppose hypothetically, let's make it really simple. Let's say this is 20 units long and this is 10 units high, my rectangle. Let's suppose we were able to calculate the area under the curve using calculus. We're going to do this next day. And let's suppose you came up with an answer of 200. Well, if my base is 20 units long, doesn't that mean there's a rectangle 10 units high that has the exact same area? So here's my suggestion. Anything I can possibly draw, there's going to be a rectangle with the same base that has the same area. I mean, that doesn't really seem like it should be a stretch. I am interested in that rectangle. So let me give you a really simple picture that you can all easily fathom. Here's a triangle with a base of 10 and a height of 20. I'd like you to tell me, does there exist a rectangle out there that has the same base and the same area? Yeah, I'm pretty sure it would be that one. Do you agree? Because the area of the triangle is 1/2 base times height. I'm trying to keep this as simple as humanly possible. Anything you could possibly draw that's bounded will have a finite area, and therefore there will be a rectangle with the exact same area. That should seem like a kind of an oh duh. But what I'd like to do, I'd like to figure out a couple things. First thing, I'd like to figure out what is the height. And in some cases, I'd even like to figure out what is the x-coordinate. Well, in my picture, I have several, don't I? I have several x-coordinates that would contribute to the same height. Let's just say hypothetically this was the one. I'll call it C. That means that this integral is equal to b minus a times f of c. Now stare at what I just wrote, stare at the picture. Do you agree with that statement? The area under the curve is whatever it is. We'll calculate that. Just make up a number in your head. 200. What's b minus a? That's the length of the base. What's f of c? That's the height of my big rectangle. The mean value theorem for integrals says there is a c out there. And in this picture, there's a few c's. It says there's at least one c out there where if I take that height and I multiply by that base, I get exactly that back again. That should feel kind of like an oh duh, because it doesn't matter what you draw, you can always come up with the rectangle. Now, we're going to figure out what the f of c is. We're going to be able to work backwards. So if I wanted to know what is f of c, if I wanted to know what f of c is, could you tell me what f of c is? Yeah, it's going to be 1 over b minus a times the integral, isn't it? I'm just dividing by that thing. So the mean value theorem for antiderivatives simply says there is a c. There's at least one c where f of c is equal to that. Now, think of this a different way. I like this version of this answer. I'm not going to erase the red yet. I want to subdivide this a lot. I'm going to subdivide this, a lot. I'm going to come up with a lot of rectangles. And I want a lot of rectangles. I want to subdivide this tons. If I calculated the height of every one of these rectangles, to the curve, not to the line. Right, if I calculate the height of all of my rectangles after I squared them off, let's suppose I have 1,000, I have 1,000,000, I have a bazillion rectangles. I calculated every single height, and I found the average of every single one of those heights. What would that number be? It would equal that. So we have another name for this. It's called the average value of f of x over the interval from a to b. I could construct a bazillion rectangles, found the height of every one of them, added them all up and divided by the number of rectangles. The value I would get is exactly what f of c is. It's the average height, because that's the height of the rectangle. Does that make some sense? It's actually the simplest geometry we could possibly perform. I'm working with a rectangle where I already know the area of the base, or the length of the base. All I gotta do is find the height. But I find the height, right, that way, or more specifically that way. So let's do an example of one. All right? Let me do an example. Without doing any work, I'm going to give you an answer. Don't even worry about where it comes from, because it's not important. Okay? I'm going to say we're going to go from 1 to 4 of f of x dx, and I'm telling you the value of this is 27. I have some picture out there. Okay? Okay. I'm telling you the area under here is 27. You notice I'm not even giving you a specific function because that's not important right now. So I would like to know what is the average value of that f of x. For this problem, what is the average value of f of x over the interval 1 to 4? Why do I have to say that? Because every interval will have a different answer. I have to give you the specific interval. How wide is 1 to 4? 3 units wide. So what's the answer?
9.
And you got that by doing what?
Dividing.
27, in fact, I'll write it like this. The value of the integral divided by the width of the, oh, okay. So that means there is a rectangle in existence with this base, and let's say it's about right there. That the, keep it simple, that's 9. That's what we just determined. Do I have to do any work? No, pretty easy. Why? Because the area of this rectangle is 27, and we said the area under the integral is 27. So the average height. So if I could subdivide this a bazillion times, every one of those rectangles on average would have a height of 9. Some are above, some are below. That's fairly simple to use, isn't it? Turns out this is a super, super huge major component for the fundamental theorem. That this average value thing takes place here. Okay? Now, we're not interested in how to calculate the integral. That seems kind of backward. No, that's a completely separate animal. I want to get into the manipulation of what I can do with definite integrals. A definite integral is a numerical value. And in Calc 1, it's usually a simple geometric thing. It doesn't have to be a geometric thing. It can represent a lot of different things. Okay? You can integrate things and get more than just simple geometric things, you know, areas, volumes, things like that. There are more things involved in that. If I integrate any rate of change, I will get what the original units were. For example, if I integrate speed with respect to time, what will my answer produce? Well, what are the units of speed?
Units per second.
Well, be more general. What is speed, you know, dollars per pound? I mean, what is it? It's distance per time. If I do distance per time, that's a rate of change, and I integrate with respect to time, I will get back distance. So that works. But can I integrate other things? Yeah, anything with the rate. So let's suppose that Has anybody ever seen the stock market ticker? You ever seen like on the news? You know, you see the ticker and it's talking about all the different prices of all the stocks. I don't know how anybody pays attention because there's so many. But let's suppose you were following a particular stock, and it's constantly changing, right? Going up and down, it's all over the place. Okay, there's a rate of change. Maybe there's even a function that dictates its rate of change. So what units is it going to be? Well, it's probably dollars per time, right? The rate of change of my stock. It's changing, going up and down, you know, maybe pennies per second or dollars per second. So if I do the integration, again, with respect to time, which is the most common unit we actually integrate with respect to, my answer will be in dollars. It doesn't always have to be a geometric thing, like I said. It doesn't always have to be a distance or an area or a volume. Those are just really common. When you're integrating a rate of change, you get back basically the numerator. Because you're integrating maybe something per time, then you're integrating with respect to time. You with me on that? That's what integration does. It undoes the derivative and gives you back the original kind of thing. And you're going to see so many versions of this. Our first association with derivatives was the instantaneous rate of change on a curve. In other words, the slope of the tangent line. But we're going to see derivatives are way beyond a picture. They're just basically an instantaneous rate of change. You're driving your car. You're speeding up. From point A to point B, can you find the average speed you were going? Yeah, you take an interval of distance and an interval of time, and that was your average speed. But as you passed that landmark, right when you went past that landmark, can you tell me how fast you were going at that moment? Yeah, that's your instantaneous rate of change. That's a derivative. That's exactly how fast you're going at that moment in time. Now, I find this interesting because I'm a big sports fan, and one of the new things they love throwing at us, because they always throw meaningless statistics, you know, it'd be like, you know, Max had the most touchdowns for anybody with curly blonde hair who was born in February. You know, that guy, they always throw really random things. But the one they like doing now is speed. Has anybody seen that where they talk about how fast somebody got to? So they'll talk about speed. You know, somebody got to 20 point something miles per hour, 21 miles per hour while they're running. They're going to give you one number. Are they giving you their average speed over the duration of the run?
No.
Why not?
It's not as impressive.
Why? Because they were starting from a dead stop. And when was the run over? Either after they scored a touchdown or they got tackled. Either way, they stopped. So if they give us the average speed, it probably isn't all that fast. But what are they giving us?
Top.
The fastest speed. So they're saying at one moment in time, they ran this fast. Did they run that fast the duration of the run? Very unlikely. Very unlikely. So I find that one really, really interesting. And the fastest I've seen in the last few years, because this is now a thing they love showing, up to 21 miles an hour, which is really fast for me and you. If that guy's running against Usain Bolt in the Olympics, you're laughing. Usain Bolt gets up to almost 29 miles per hour, which is like one guy sprinting and the other guy jogging. I mean, it's not even comparable. This is not close. It's Poe. Okay, so when we talk about instantaneous anything, instantaneous is always a derivative. By the way, when we're talking about these things, are we all picturing a graph and a tangent line? Probably not, right? How many have had a business calculus course? Is anybody here, you started in business calc, you ended up here? Usually there's a handful of people. In business calculus, everything's about revenue, profit, cost. But you're interested in instantaneous. It's called marginal. You guys have ever heard the term marginal? Marginal cost, marginal profit, marginal revenue. That's the instantaneous rate of change with respect to time. How fast are my units moving? How fast are we making money, you know, with each additional unit? Okay, so that is a derivative, and so everything is about the integrating of those things, because that's the most important thing they study. We start with derivatives and then we work backwards. But the term marginal refers to it's an instantaneous rate. But there's no picture, there's no tangent line, right? That's our initial. So right now we're going to get into some pretty heady stuff. The stuff we're doing today algebraically should not be that nasty. Now on the quiz associated with today, I broke it down into small pieces. I think the first question is, tell me the area of the rectangle. There's no calculus, just what is the ith rectangle? Not only do you have it in the notes, I think I have a video, I also have lecture notes that have the exact same thing. Then I'm going to say, now give me an estimation for the overall area. Now tell me what it is using a limit. Now you got to use those summation formulas because I'm giving you a simple polynomial. I'm going to ask you, I think, for the Riemann sum, which doesn't require work, it just requires that I write limit of the partition. I'm going to ask you for the definite integral. That's the easiest one. You're just writing down the definite integral. Do you know the value of the definite integral? Yeah, because you computed it earlier by taking the limit of the rectangles, which is a lot of work. But you need to see the entire picture because the next day we're going to be able to put it all together and I'm going to show you how to do these things at light speed. You're going to like that better. Once we developed the derivative formula after all the limits, you liked the derivative formula a lot better, didn't you? Right, we used the limit to do x squared and that was a lot of work. So what if you want to do x to the 10th? Nobody here wanted to do x plus delta x to the 10th power, expand it and then go from there. So once we developed the formulas, you realized you could do everything super speed. But we had to get there first. So this is the getting there. This is the last of the stepping stone lectures, really for a while in any of the calculus classes. My Calc 3 has done a couple of these recently because they had to learn how to do multiple integration. So we went all the way back and everything was summations, just so you know. Summations and Riemann sums. And then we took limits, and now they can do a double or a triple integral because we did the setup. Once you know the single integral, you'll be able to do all the other things in time. Okay? All right, that's where we are.